let's begin. We were, I believe, in the middle of talking about the change of basis between momentum space and position space. And so let me just briefly recap what was going on. And let's finish up by noting that, in fact, that's going to give us Fourier transforms. Okay, so change of basis. So from position space, position to momentum representation, and we'll find that that's the relation to the Fourier transform. Fourier transform is, in fact, the change of basis from momentum to position representation or backwards. So that's basically what the Fourier transform is. So let's see explicitly what is going on. So remember that position representation just means we're working in the basis where we're using the basis where it's an eigenstate of the position operator. But because translations itself is unitary, and you can write it as d dot momentum, where this is permission, therefore, there must also be eigenstates of the momentum operator, which we call K, which we are calling K. Okay, so this is just a brief recap. But once you recognize that these observables do not commute, xi, pj do not commute. In fact, we derive the commutation relations. This was not an independent postulate. We derived this based on the properties of what translations meant, and based off the fact that P is just the infinitesimal, the generator of infinitesimal translations. We're able to derive this. So because they're not compatible, there's the question of what this guy is. And what we discovered was that this was just a plane wave, e to the I k dot x. Okay, I won't go through the derivation again. But it comes out with the observation that these are not compatible observables. And because they're not compatible observables, we therefore must have a way to change basis between the two. This is an issue. But once we have this, then we see what happens is that when you start with a position basis, then you want to change into the momentum basis, and what we do is just insert a complete set of momentum eigenstates. Right, so this is just a completeness relation. But now we know what this guy is. Kx is just a complex conjugate of this guy. So what you see is that the position eigencat itself is just the superposition of all the momentum eigenstates integrated over e to the minus ik dot x. Minus because we're taking the complex conjugate of this. And you can ask the question, how do I go backwards, right? How do I go from k to x? So in this case, we insert a complete set of position eigenstates. Okay, so this is the identity. By the way, I think, I don't know if I said this before, but I should emphasize that, or you should really be asking me, why is that 2 pi d below and not a 2 pi d here? So the reason is that this is an issue of convention. So if you choose, so basically the total number of 2 pi should be the same. You should, if you have 2 pi d over 2 here, you'll find that you get 2 pi d over 2 over here. But my convention is that I'll put all my 2 pi d's in the k integrals, and so I will have no 2 pi d's in the x integrals, right? And so this is just convention. Where you put down is convention. But I thought I should mention this. So I have a completeness relation by integrating over all the position eigencats, cat-bra operators, and now k, xk is our plane wave. So this is now the integral over all positions integrated against e to the I k dot x. Okay? Yes. So, so let's see what happens when I project. So these are the eigenstates. Okay. But once I know how to do this, then, for example, I can convert between, let's say, my wave function or my state written in the position basis, and now I can ask the question, how do I convert it into the momentum basis, right? Well, I can insert a complete set of states if I want, or I can say, well, I know that that's how I convert between x basis and k basis, so all I have to do is just project psi on both sides, and then take the complex conjugate, right? So if I apply psi over here, I take the complex conjugate, I get this guy. If I apply psi on here, I get psi k, and then when I take the complex conjugate, then what I get is integral over k. And then k psi, remember I've taken the complex conjugate, and so here it will become e to the I k dot x. Okay. So what usually we do is when we talk about a function of x, then we stop using the bracket notation. Right? Usually what we do, we end up saying that this is just psi of x, and this is in momentum space. Usually we call this psi tilde of x. It's just a definition. The tilde just means you've gone to Fourier. I've gone to Fourier space, psi of k. And so if you write it in that language, then you would just say that psi of x, in other words, psi, a state in the position basis, is just psi of k, psi tilde of k, integrated against the plane wave. Right, so this is a superposition of plane waves these are the Fourier modes weighted by psi tilde of k. Okay. So if you had no weight, if it was a uniform weight, then you get a delta function. In other words, it's like I think that's what they call white noise, right? So if you have a pure, equally weighted spectrum, so to speak, every k has the same power, so to speak. Then when you integrate over it, you get the delta function. But no such signals like that, right? Every wave function has some peak over every signal or wave function or whatever you're talking about. Anything physical usually has a finite bandwidth, and therefore psi of k, psi tilde of k, is usually non-trivial. Right? It doesn't even matter whether you're doing quantum mechanics or not. Anything physical usually has a finite bandwidth, and that's basically that's what this equation is telling you, that to understand a signal, you need to understand all the wavelengths. Right? Let me just write it down. It's a decomposition. Decomposition of a signal into its normal modes, into its modes of wavelength, each of wavelength k is roughly, in fact I think it's not roughly, it's 2 pi over lambda, like if you want to be precise. Usually I just don't care about the 2 pi. But heuristically, you just remember k goes like 1 over lambda. And then likewise, you can go in the backwards direction, starting from this guy. I can project psi on k, and then psi on x. And then I just take the complex conjugate. So what I get is that psi of k, which is what we've been calling psi tilde of k, is now the integral over position, and then this is now x of psi e to the minus I k dot x, and then in terms of sort of more ordinary calculus language is dx psi of x e to the minus I k dot x. Okay. So this is the Fourier decomposition in plane waves. This is the inverse transform. Right? So this is the inverse Fourier transform. So this invertible. This is an invertible transformation. So just as we, so remember this, just as we, in the finite dimensional case, maybe I'll do it over here. In the finite dimensional case, really, this is the vector, right? It's a superposition over the basis vector that gives me the vector or state. But very often we just look at the components and we call this the vector. Okay, so this is a component, but these are the components, but we usually get a bit sloppy and we just say that once you've chosen a basis, this is the vector. So likewise, when you are actually doing practical calculations, usually that's how we think about it, which is that x can be any state, including the basis, can be superposed in terms of k, but weighted by the plane waves. right? So very often in a sloppy way, we can call that these guys, so likewise, we call these guys the plane waves, the basis functions. Okay. So again, these are the bases. Either you use x or k. If you want to be very strict from the linear algebra point of view. But in the more intuitive sense, just as we call the components our vector, these are the components, but these are also our basis functions. Okay. Any questions for me? You know I took a video of this guy, right? So, and we have notes on this as well. I prefer that you try to understand what I'm saying in class, and then try to ask me some questions, right? I mean, I'm not going to stop you. You can take all your pictures, all the pictures you want. I don't mind. I'm just saying that the material I put on the board is usually redundant in the sense that usually I take either videos, and actually all of it, you can find it in some form in my notes. Right. So what I really prefer is that people follow along what I'm trying to say and use this opportunity to ask me questions. Right. So I know where you are, I know whether you are understanding what I'm saying. Okay.
So you say that the psi k is the vector.
Psi of k are the components, right? So certainly it's true that psi tilde of k is k psi. And so if you're decomposing psi in terms of the Fourier modes, then these are the components of your vector. Is that your question?
So, is that what you say that is the psi k is the vector? Does and
That's what I'm trying to ask you, right? Are you pointing this out? Is that your question? I'm not sure of your own question.
The k is the basis function here.
That's right. So the k is the analog of I, right? You're talking about this one, am I right? Yeah. So the i's are the basis, except that we started talking about the discrete case, right? Now we have a continuous basis, but this k is the I, and the v are the components, and here the components are the continuous components. Psi k psi is are the components. Right? Yeah. So if that's your question, yes, that's exactly right. That's exactly right. Yeah. And likewise, likewise, the x psi are also the components, right? But now in the position basis. And the Fourier transform is just the change of basis. Okay. There are no questions. I'm going to move on to the uncertainty principle. something we haven't talked about, right? So we know that, so I think I wrote it down over there. We know that X and P are not observables. Sorry, they're not compatible observables. So that means, if you recall, there is in fact a uncertainty principle that we derive in a very general sense, where the expectation value of delta A, I better call it delta A because in my derivation I call it delta X, but now X is our position operator. So delta A, remember, is the operator A minus the expectation value of A with respect to the same state. So this guy times delta B squared is in fact greater or equals to 1/4 the square of psi commutator of A comma B squared. Okay? So this is a very general statement that we derived maybe last week or the week before, I think. And now we can apply to our situation over here. So if we take the first component, so it's a little bit confusing if you think about it, because we have I and j runs from 1 to d. So what do we do, right? So let's take I equals to j equals to 1. Right? So for sure, you can write that, actually, let me just take I equals to j. And then so what it means is that, what does that mean? It means that psi delta xi squared psi times psi delta pi squared psi. Right. So this is now I is fixed. Okay. It must be greater or equals to 1/4 the square of psi commutator of xi pi psi squared. Well, this guy we know x comma p according to this guy is just I. Okay, if I is equals to j, it's just I. So if you square it, if you square the thing, it's just 1. So it's greater or equals to, same thing, 1/4, it's just 1/4. But we have many dimensions, right? So I is just one dimension. So you can sum over all your dimensions, and therefore, so now you sum over I from 1 all the way to d. So it's an inequality, but if left-hand side is greater than right-hand side, for all the i's, then you can just sum over them, right? So what you get is you now get sum over psi delta xi squared psi delta pi squared. Okay, and then the sum over I is now greater or equals to sum over I 1/4. Well, it's just 1/4 sum over itself g times. So this, easy to see, this is just d over 4. And this guy is just delta delta x squared psi I am using the fact that it's a Kronecker delta. Yeah. Yeah, so that is a general uncertainty principle. Let's do it over 3. 1, 2, 3. Okay, because we live in 3 dimensions. So let me just do it over 3. So in other words, the uncertainty principle depends on the dimension. If you care about the total variance, right, not just in one dimension, but the total variance of the position and momentum operators, how are they related? Okay. Any questions for me? Yes.
I equal to j in that function. It is larger than 1 over 4. Y is not larger than negative 1 over 4.
Negative 1 over 4. Negative, sorry, I didn't understand that part.
Because x p commute is I. I
Yeah.
square is negative 1.
No, it's an absolute value. Absolute value, yeah. Yeah.
But we take absolute and square.
What's the absolute? What's the absolute value of I?
I.
Yeah, what's the absolute value of I? What does absolute value mean? Length of the complex number, right? That's what it means. So I means, it just means you're going 1 unit up on the complex plane, right? In the imaginary direction. But the length is 1. That's basically it. Yeah. It's not a square, it's an absolute, it's the length, the square of the length. Yeah. Good. So in your homework, you'll discover that Gaussians are special exactly because they saturate this bound. Okay? They saturate this bound. So what do I mean by that, right? So what I mean is that if you plug in for psi, let me just write it down here. Gaussians saturate the uncertainty principle. So what it means is that if you use Gaussians over here, so it's x psi is Gaussian, meaning is proportional to e to the minus x squared over to d squared. D is just a length. Okay. You would find that that delta x squared psi delta p squared psi is in fact 3/4. So instead of being greater or equal to 3/4, in fact in d dimensions it will be d. Okay, you should find this through a direct calculation. Let's do some integrals. Okay. this is also why, I should say, this is related to the fact that when you go to Fourier space, you find that this is also the Gaussian. I believe these two facts are related to each other. Right, so sometimes you hear the Fourier transform of the Gaussian is a Gaussian. And I believe these two statements are related to each other. Yeah. Although I won't elaborate on it, but I believe that they are related. Okay, so the next topic that I want to talk about is that of degeneracy. Because as I told you guys before, in quantum mechanics, the notion of symmetry is very important. Actually, it's more important than in classical mechanics, the notion of symmetry. And because it holds at a fundamental level, the way we understand the physical laws in our universe, which are quantum in nature, is true with symmetries. Right? But, so I want to say a few words about that. And then later on, I will see how it's broken, in fact. All right. So what the heck am I talking about? So, I'll put, since it's a quantum mechanics course, so I'll talk about it in terms of quantum mechanics. Right. So the free particle in non-relativistic quantum mechanics, for once I emphasize non-relativistic quantum mechanics because the answer is a bit different in relativistic quantum mechanics. But for now, let's just focus on the non-relativistic case. Okay, and the answer is that the free particle in non-relativistic quantum mechanics is simply governed by its kinetic energy. So because free particle means there's no potential, right? So this means no potential energy. And so that means that the Hamiltonian, if you've taken a classical mechanics course using Hamiltonians and Lagrangians, you will know that kinetic energy in Hamiltonian language is p squared over 2n. Okay, so this is in fact this kinetic energy. And so, in case you're not familiar, we'll just write down half mv squared and convert it into p squared. And you'll find that it's actually p squared over 2n. But remember that the reason why we do this in quantum mechanics is because we can now ask the question, how do we diagonalize? How to diagonalize H. So we've been spending all this time talking about the fact that K are the eigenstates of P. So if we know how to diagonalize P, So we surely know how to diagonalize p squared, right? So what we will discover very soon is that this is not always true. It's not always true that we can diagonalize p, or rather p squared over 2m, by diagonalizing p. Okay? But in this case, we can. So in fact, we see that h acting on the momentum states is in fact just p squared over 2m acting on the momentum states, and that gives us k squared over 2m. Okay, so that's easy enough. So energy, the energy of the free particle is just given by a continuous label. Right, it's just given by the momentum, and it's just k squared over 2m. So what I want to point out is that there's an infinite fold degeneracy. Why? Because momentum, you see, energy just depends on the length of the momentum squared. Okay. And that means that basically you can have any momentum you want as long as they have the same wavelength. Right? K goes like wavelength. As long as you have the same wavelength, you have the same energy. And in particular, you can go in any direction you want, and it will still be the same. It will still be the same energy. It will still be the same energy state. Right? So this, I claim, is due to the high degree of symmetry. So let me just say it in words. Same E for any K with the same length. Right? So in other words, you can point in any direction and you get the same energy. Of course, that is a result of the fact that this is a rotationally invariant system. Right? So we'll talk about this a bit more. But this is also a fact that this is also a consequence of translation invariance, I claim. Right? So this is, so you might think that this is rotational invariance. But there's also translation invariance here as well. Let's see whether we can understand this. Right? So what is translation invariance? So E to the, so let's consider T acting on K. Is it a good way to talk about this? Okay, maybe I'll save this for later. But rotational invariance is certainly clear. Okay. So why is that so? Because if I rotate my K in some other direction, it gives me the same length, and therefore it preserves the energy. Right? So let me just say this: symmetry implies degeneracy. This is something I've talked about before, but I just want to remind you guys of this. And in fact, what you'll discover is that it's not true anymore once you break the symmetry. So in fact, we expect degeneracy to be broken. Once rotational symmetry is broken. So how do you do that? One way is to put the particle in a box in a fixed domain. So if you think about it, locally, if you put a free particle in a box, so where the box has it does not exert an external force on the particle, except maybe at the walls, right? So how do you do this? So let's rotational symmetry. One way put system in a box. So I'll just say it is in a finite domain, right? So because it doesn't really need to be a literal box, just a domain that's finite. So at the walls, the fact that the wall means it exerts a particle on the force on the particle, so that the particle cannot get out, right? Or whatever system, whatever quantum system you have. But inside is free, right? So inside V is 0. The potential is 0. And so H is still given by P squared over 2M. But what you find is that locally, so if you only look at this little region of space, yeah, it looks rotational invariance for sure. You can rotate it around, it looks the same locally. But this is one place where you discover that the global characteristic of the system is important. In other words, what you find is that boundary conditions matter. Okay. And in this case where, because there's a finite domain, if you rotate the domain, it's not the same thing anymore, right? This thing is not the same thing as if you rotate it like that, or you rotate it this way. So once you have a boundary, it selects for you kind of a special reference frame, so to speak, right? Our classroom is an example. We rotated the classroom by 90 degrees. It's not the same classroom anymore. If you turn it around upside down, then that's not very good, because then I can't read my own writing anymore. Right? The writing will be upside down. It will look different. The floor will now be the ceiling, and the ceiling will now be the floor. And so it's definitely a different classroom. Right? I don't want to walk on the ceiling. I want to walk on the floor. Right? So it's different. And even though, again, if I just focus on a little region of the classroom and I rotate it, I can't tell the difference, right? I can't tell the difference. But if I take the whole classroom and I rotate it, then I can tell the difference. It is, in fact, different. What we're going to discover is that boundary conditions matter. Right? This is a heuristic. I'm being a little heuristic here, but let's try to make it a bit more precise. Okay. So the first question is, what kind of boundary conditions do we need? Right? Not just related to the question of rotational symmetry, but also about the chronicity of the Hamiltonian. right? So not just for symmetry. In other words, boundary conditions do not just affect the notion of symmetry, but also affect the hermicity of the Hamiltonian. In this case, it's T squared. Okay, this is something that I'm going to talk about. Yeah, you have a question for me?
I can understand why the symmetry break if the class was upside down. So
yeah, because it's not the same classroom anymore, right?
So the rotational invariances come from the coordinate invariance. So I mean,
No. Be careful. Yeah, no. Be careful. So of course, yeah. So that's always a tricky point to think about, right? But yeah. So don't be confused by coordinate invariance versus symmetry, right? You can use any coordinates you want to describe the system. That's coordinate invariance, and that I completely agree. But that does not imply, that most definitely doesn't imply that there is invariance under whatever coordinate system, whatever change of coordinate system that you perform. Because that would actually mean that there's all kinds of symmetry, right? Because you can change your coordinates to anything you want, but does that mean that that change corresponds to a symmetry? Right? So that's the two things that you want to be very careful not to be confused about. So again, turning the classroom upside down is not, there's no rotational symmetry over there because you can tell the difference, right? That's how you tell. Is there a symmetry or not? If I take a ball, and the ball is just perfect, right? The surface is completely smooth, and I just rotate it, then there's no way I can tell, right? If you just, cover your eyes and I rotate it, or if I pretend, I tell you I rotated, but I actually didn't, right? I lied to you, I didn't, right? You can't tell the difference. Whether I lied to you or I actually rotated the ball, right? That's symmetry. But if I turn the classroom upside down, you will be pretty sure that I turned the classroom upside down, right? Because the table will be on the ceiling, and then you can't read the board because it's now upside down, right? Because relative to where you were, there is now a difference, right? So there is, it can get confusing, but be careful not to be confused between general covariance, which is the statement that physics should not depend on what coordinate system you use, because that's it's a human construct, but very, very important construct, but it is a human construct, right? Whether we use Cartesian or spherical or symmetrical or whatever, versus a genuine symmetry of the system. If I take a ball and I rotate it, I can't tell. But if I turn the classroom upside down, I can tell. There is a difference between, as long as I stay put and you turn the classroom upside down, then I will be able to tell, because things will look very, very different from before, right? And that's what I mean here. By boundary conditions, I really mean, can you tell on a global scale? So boundary conditions and sort of large scale, on the large scales, right? That's what I mean by boundary conditions. But it's not really specific to just boundary conditions per se, but just on the large scales, can you tell? Usually on the small scales you can't tell, but on the large scales you can. Okay? But I also want to use this opportunity to show you that the reason why I highlight boundary conditions is that they will be very specifically affecting the hermicity of your Hamiltonian, right? So let's take a break first, but But after the break, I'll show you. I'd like to encourage people to ask questions because whatever question that you have, maybe other people will have the same question as well. Okay? Certainly, stop me if you try any typos or whatever. Okay? Okay, so let's come back to this question. Is P permission in a finite domain? So remember that permissivity is important because if your kinetic energy depends on P squared, then you better believe that P squared is permission. Otherwise, you're not even guaranteed that your free particle energies are real, right? So that would be a bad thing. Somehow your free particle doesn't have real energies. How would you even interpret your quantum mechanics? Right. So it's important. It is in fact important that is permission. So what is hermicity? So suppose you have P. So suppose you have you calculate the matrix element of P squared, right? If it's permission, it means that the complex conjugate of this matrix element is just psi 2 P squared psi 1. Okay? If it's not permission, you will have to put a dagger around P squared. But if it's permission, then you're okay. So this is in fact the place where I should mention, this is one place where the Dirac notation is not very good. Because it hides the fact that I want to emphasize to you guys now is that hermicity effects is very much affected by the boundary conditions. When you're talking about continuous spaces and when you're talking about continuous operators such as P squared. And so let's see why that is the case. So let me just make a side remark. Dirac notation hides the need for boundary conditions. BC. BC means boundary condition. But let's see. Okay. So the way to see this is that we need to insert a complete set of position states between these guys. Okay, so let's do that. So hermicity means the following. So best to do it in best to do it in position space because we're doing it in we're talking about the boundary conditions. Okay, so what does it mean? So let's try to insert the complete set of eigenstates in position on the left-hand side. So if I do an integral, now remember I'm in a finite domain. Which I'm just going to call detailed. Okay, so this integral now takes place in this detailed, and so, but I can still postulate that I have a complete set of position bases. It would be very strange if it's not true, right? Because that would mean there's some hole in your space or something like that. But even then, you just cut out the hole and you just don't consider it in your domain, right? So I think you're almost always guaranteed. I believe you're always guaranteed a complete set of bases position eigencans. So P squared, what is that? It's just a Laplacian. So this is now really asking the question, this is sine 2 and x. But I'm going to take the complex conjugate. So this is now sine 2 at x star. Okay? And this guy is the Laplacian, minus Laplacian acting on psi 1, but I take the complex conjugate, so now it's minus Laplacian of psi 1 x. Okay? So that's what the left-hand side is. Let's look at the right-hand side. The right-hand side says that. So again, I insert a complete set of states in the same way. Just want to make sure I got the numbers right. Yeah, 2, 1, right? So now, that's easy enough. So this is now integral over my domain, and this is minus Laplacian acting on psi 2 star okay, that's this guy here, and then this is psi 1. So if you compare the two expressions, what I've done is, what the difference is, not what I've done. What the difference is that basically I've integrated by parts, right? So this guy, this Laplacian, is now on this guy instead of 1, right? So here was 1, here's 2. So basically, there's a difference of integration by parts. If you just think about it in terms of calculus. But is it really true? So let's do it. Right? Let's use calculus instead. So use calculus. And start from right hand side. Or left hand side. Let's do left hand side. So left hand side says, remember this means is Hermitian. Now, let's start from there. So integral over x over the domain. And now let's try to integrate by parts. So if I do it once, what it means is that I will now have a boundary term. So in the math jargon, partial d star, d tilde means the boundary of d tilde. Right now I'm completely agnostic about what my boundary looks like, except that it's there, right? It's a finite domain, so there is a boundary, but I'm not going to specify exactly what it is for now, because it's quite general. And what you find is that you get d minus 1 sigma. I call this is like dA, right? So this d sigma is like dA in vector calculus, right? Dotted into what? Dotted into, if you integrate by parts, sine 2 of x, and then minus gradient on psi 1. And then when you integrate by parts one of these guys, you get minus, remember you pick up a minus sign, actually you pick up a minus sign, so this guy goes away, plus integral over the domain dx of grad psi 2 star dotted with grad psi 1. Okay. Star. Let's put a star. Remember, my star is the same as my bar. I can integrate by parts again. Okay. And what I get is, let me not forget my boundary integral. If I integrate by parts, I'm going to move this guy over there. So what I have is now rad psi 2 star coming from this term times psi 1. And then I don't want to forget this term, minus psi 2 star rad psi 1. Okay, so this and this term. And then when I move this guy over here, I get minus or e plus integral over the domain. Now minus Laplacian acting on psi 2 star psi 1 over the domain. Okay. In other words, I start from the left-hand side, I integrate by parts twice. Right? And that's why I have two terms, because I integrated by parts twice. And this guy, if you compare with this, is exactly the right-hand side. This term is exactly the right-hand side. But I have some extra terms. Right? In other words, what we're discovering is that the math of it tells us that it is not automatic that p squared is Hermitian. Why is it that it's not automatic that p squared is Hermitian? Because if you actually go through the calculus, you'll find that you always get this extra terms. So Hermicity is not a free lunch, right? It's not a free lunch. Hermicity is something that you have to impose. You have to make sure that your system obeys Hermicity. Otherwise, you won't get your real eigenvalues. So let me point out two ways to do it. There are probably, I'm guessing, probably infinite ways to do it. But let me tell you the two most common ways to guarantee Hermicity or to impose Hermicity. Okay, let me erase this part first because so the first way to do it, the first type of boundary condition really is known as the Dirichlet boundary condition. Dirichlet, okay, I can't guarantee you that I spelled it right, but it just means that you demand that when, okay, hopefully it works. All right. Any questions for me so far? So again, it's a very general statement, right? But you see that boundary conditions is what would make this surface term vanish, and that's how you're able to move the Laplacian from this guy to this guy, and that's what makes the Laplacian Hermitian. And p squared is just the Laplacian, right? And that's what guarantees the hermicity of your kinetic energy. So even if you have a potential inside your domain, you still want your p squared to be Hermitian, right? Having a v doesn't change the fact that you need it to be Hermitian. So this statement will still need to be true, right? The boundary conditions still vital, even if it's not a free particle anymore inside, even if you have a non-trivial potential. Right, so just remember that. But now let's try to solve some simple examples where you can now tell what the actual energy levels are. And like I said, you will discover that the energy levels are no longer as degenerate as they were before for the infinite space. And also I want to say something about translation symmetry. Yeah. In this course, I want to emphasize the symmetry concepts because I feel that that's what the spirit of Weinberg's book is. If you read the book, I think he does try to emphasize this aspect, and I'm trying to do it in kind of my own language, but following Weinberg's spirit. Maybe I'll say that first, because I know I only have 15 minutes or maybe 15 minutes, 20 minutes. Right. How much time do I have? 15 minutes, right? Yeah. So let me just say that first because I want to emphasize the symmetry properties. Note, translation is no longer unitary in a finite domain. Okay. And you know that we've talked about this before. If t, remember t is the exponential of the momentum operator. So this is always true. Why is this always true? Because it actually generates just a Taylor expansion on your wave function. But if this is not unitary, so if this guy is not unitary, I haven't explained that, but I will very soon. Then in fact, P is not Hermitian. Remember that we showed that this was unitary if and only if, in fact it's quite general, that if you have an exponential of an operator, and if the exponential, the whole thing was unitary, the generator is Hermitian, and vice versa. So if this is not unitary, then in fact, you will see that P is not Hermitian anymore. So this is quite subtle. All we have done is we've gone from an infinite domain to a finite domain, right? It could still be no potential, it's still a free particle, but just by that, it's not unitary anymore. So why? So why is it? Yeah, why? And the answer is that we've broken the translation invariance. Is broken by the boundaries. So the best, the simplest example is to just consider the one-dimensional box. Okay, if I'm over here, the walls are over here. So it does make a difference where the walls are. If I don't have walls, if I have an infinite domain, then I cannot tell where I am, because space is empty, right? There's no distinguished origin for one thing. But now there are walls. Well, it makes a difference. The walls here or the walls here, right? It makes a difference because it tells me how far I can go. if the walls are here versus if the walls are here, it makes a difference. Okay, so this breaks translation invariance. Or one way to put it is that there is now a privileged origin. There is now a privileged coordinate system. Coordinate system, or let me just put it, origin. Why? You can't put the origin here for one thing. It doesn't make sense. It's outside the domain. The origin has to be somewhere between this wall and that wall. Otherwise, like I said, it makes no sense. Doesn't really make sense. And your space only runs from 0 to whatever the length is, which I'm going to call L. Right? You can't go beyond that. So let's make it even more concrete. So remember that I think this you did in your homework. You showed that there is a way. Let's do it in 1D, right? So I just have just one parameter D, and you showed that you can construct a translation operator by going by summing over all the old bras integrated against all the new cats. Right? So this is the new basis, and this is the old basis. Remember. I think this was one of your homework problems. I think the homework problem was to show that this actually implements translation and it was unitary, right? Is that true? Have you guys done this problem already? Or I forgot. I think it's in your current homework, if I'm not mistaken. Right? This is unitary in infinite space. I should add infinite flat space. Okay? But what do you do here? Let's think about how you would do that. So how you would do that is you would try to do the same thing. You would say, well, let's try to do sum over from 0 to L, right? And then the old basis is just the x. And the new basis, well, okay, x plus d. That's what you would think you try to do. That's a natural guess, right? So, but I want to put a question mark. So what kind of trouble will you run into? So what you find is that it's all fine if both x and x plus d are inside this domain. But for example, let's say, what happens when x, the integrand x, approaches L? So what you have is then you have x plus, you have something that goes from L plus d, L. Right? In other words, this term will show up in your integral. But you see that this makes sense. This is a localized state very near this boundary. But this guy makes absolutely no sense whatsoever, because this is now somewhere here. This is a state somewhere, localized somewhere over here, to the right of the wall. Right? Because if you can construct this guy, then you have shown that this is unitary. But you can't. Okay, you can't, because you can't. There is no such state here anymore. Right? L plus D doesn't exist anymore. In fact, you can't plug in anything bigger than L minus D. Right? If you plug in anything bigger than L minus D for X, this cat makes no sense anymore. Let me just say, this makes no sense. So you cannot construct, mathematically, you cannot construct a unitary translation operator in the same way as you did as before. But of course, just because you can't do it doesn't mean it cannot be done. Maybe there's some other way to do it. So the ultimate answer is just remember that because you have a domain, it makes a difference whether is it here or is it here, or is it there, right? If you move your box, you move your box, right? I can tell that the box was here, was not there, it was here. So just having a domain changes the fact that whether something is symmetric or not, right? And therefore, in turn, breaks it breaks the notion that translation is just a change of one basis to another basis without any privileged set of bases. But here there is a privileged set of bases. It's the localized states from 0 to L. Nothing else. You cannot allow for anything else. Right? No other, so you can only have 0 all the way to L. Right? That's if I choose my coordinate axis to start from here. It can only go from 0 to L. No other x allowed. Yeah.
In the case of a periodicity,
Yeah.
you have a perfect crystal, and
Yeah.
there's a potential, and you have domain, distinct domain continuously.
Yeah.
So in that case,
Yeah.
the translation vector be
Yeah, it is unitary again. Yeah. So good, very good. Yeah. So that's the next example, actually. Yeah, very good. So if instead of a finite domain, so how about let's say this is a setup 1. Okay, this is all to illustrate the notion that boundary conditions are important. Okay, so setup 2. Instead of finite domain, let's do periodic domain instead. So what does that mean? It means the following. It means, in fact, that x, let's do it in 1D, okay, just for simplicity. It means that x plus L, in fact, can be identified with x. In fact, usually we just say it's equal. Sometimes you put a phase, but let me just make it simple and say that x plus L is in fact x. And the easiest way to think about this is to just put it on a circle. Okay, and so why? Because let me just do it both ways, right? So this is from 0 to L, and then this is 2L, 3L, and so on. And now this condition that a sharply localized state at x is the same as a sharply localized state in x plus L, which means that this whole domain is basically the same as this domain, which is the same as this one, and so on. Well, if that's the case, then I can just imagine that I wrap this whole thing up on a circle because I may as well say this is 0, and then as I traverse around the circle by L, then this is my domain, right? This is this one domain. If I make another round around the circle, that's the next one, and then the next one, and the next one, and the next one. Well, anyway, they're the same. So I may as well just view it as a circle, right? This is exactly the same thing. Okay. So, and you can just imagine that the radius is given by right, 2 pi r is L, right? So radius is given by L over 2 pi. Exactly the same thing. And this guy, so since I'm talking about this guy allows you to also see that periodic 1D periodic domains, or let me just say translations on 1D periodic domains is the same as rotations on a circle. Because it's exactly the same. This circumference is one domain. We'll do it another time, it's the next domain, and so on. Right? So as I move in my domain, I'm just rotating around the circle. Right? And so therefore translations is equal to rotations. And now, in fact, we can show explicitly that the same construction will work and I can choose to just integrate over 0 to L or basically over any one period, essentially. It doesn't have to be, in fact, 0 to L. You can go from L to 2L if you want, because any things are periodic. Right? But this is the new basis. You integrate, you want to shift it by D, so this is the new basis. You take X and you shift it by D, and then you integrate against the old basis. Right? Remember, the unitary operator is always sum over new basis, old basis. Right? And this, once you can get it to this form, you should check it for yourself that this does implement translations. And then you can find that now there's no longer any problem that we had over here. For example, what happens when X is L? When X is L, it just means you have gone on to the next domain. But that's okay, because the next domain is the same as the domain that you were just in. So you're just back on the other side of the circle, essentially. So there's no problem. This lies in your space, in the Hilbert space. And there's no problem. And in fact, this is unitary. And in fact, as a result, momentum is again Hermitian. So it's quite subtle. It looks like all the symbols look all the same, right? But that's where you need to really have a good conceptual understanding of what the heck is going on, right? In the finite domain case, again, the box is here. It's not over there. It's here, right? So translation is no longer unitary because there's now a privileged set of basis vectors. In the case of periodic domains, again, there's no privileged set of vectors. I can rotate this. I can't tell the difference because this is a perfect circle, right? This is like the circle analog of the sphere that we were talking about. I can rotate this circle. I cannot tell the difference whether you rotate the circle or I lie, right? I can't tell the difference. So that's why this is now going from a completely unspecial set of orthonormal bases to another completely unprivileged set of orthonormal bases. And that's why when you sum over them, it gives you a unitary operator. And as a result of that, remember that this always is the exponential of I dp. As a result of that, P is Hermitian. Right? I did it in one dimension, but if you try to generalize it to higher dimensions, you will see. We will see. In fact, next time, I know I'm out of time. Next time, we'll explicitly construct the solutions, and you'll see for yourself that P is Hermitian, and the eigenvalues are all real. Right? We'll see that explicitly. In fact, let me just tell you that you'll find that, again, here the eigenvectors, the eigenstates are just plane waves again. and the eigenvalues are again k, but because it's the only difference, the main difference is that because it's periodic, the k, the momentum is now discrete, right? In the empty space, in infinite space, k was continuous. But now, if you're on a periodic domain, the k will now become discrete. But other than that, p is again Hermitian. T, the translation operator, is unitary. But once you're in a finite domain, it's no longer true. But because of the boundary conditions, if we impose either Dirichlet or Neumann, P is not Hermitian, but P squared is Hermitian. Because we have imposed the right boundary conditions to ensure that kinetic energy gives us real eigenvalues. Any last questions?
Oh, the box for
Yeah.
the translation
Yeah.
errors. I still don't understand.
If I put a box here, it's different if the box is here.
Yeah, I know. But
So that is the
if
breaking
there is a
of,
particle in it, it may not know it.
it will hit the wall and cannot go any further. Right? So there's a privileged set of domain that is residing in. That's what it means by, right? So if you don't have a wall, then the particle cannot tell whether it's here or there. There's no markers to tell it where it is, right? But if there are walls, then it can tell because it cannot go beyond either this wall or that wall, right? Yeah. So having a marker breaks that translation invariance. That's why. That's how I started talking about it. But boundary conditions matter a great deal, right? But once you go in the periodic domain, then again you can't tell, right? Where you are on the circle, you can't tell, and that's why you recover in a different way. You recover translation invariance. Yeah. Okay. Good. See you guys on Thursday.